This begins EE 544 with Professor Zahid on Thursday, January 23rd, 2014.
Thank you, Jay. Good afternoon, everybody. Let's continue our discussion from last time. There are a couple of charts from the first set, from the overview that I did not have time to go over it last time. I just want to go over it very quickly before we start with the second set. And the first one is identifying what are the problems or the requirements or specifications that are associated with design of any RF wireless system. Any RF wireless system consists of what? You define requirements, you define what? Specifications, we call it a what? A spec. You always start with what? The customer will give you what? Will give you a requirement. He will give you a requirement. What are they looking for? Clear? And some spec you need to what? You need to create a spec. Spec means what? Power amplifier, for example, amplification, power gain is such and such. Frequency of operation is such and such. These are called what? Specifications. Algorithms, what you are going to be doing to do what, for example, modulation or demodulation, all of these are algorithms and parameters that the development team uses to design both the hardware and the software. In any company, by the way, you will see what RF engineer, systems engineer, software engineers, they work together as a group. Does not mean that each one knows exactly what the other one is doing, but they need to have some overall picture clear in their mind so that they can integrate their efforts. So the documentation include what? The system level requirement, the system architecture. One of the first things that you need to decide is what type of receiver or transmitter architecture are you using. Is it super heterodyne? It is what? Is it direct conversion or zero IF? Is it low IF? Is it SDR, software defined radio, and so on? So all of these types of architecture. And then when you design your system, you are going to what? Include the analysis and simulation to see if you have satisfied this spec. If I show you, let me show you, jump here a little bit with me so that you understand what I'm talking about. This is the design flow. I will tell you where the 544 fits in. It's the system specification. You start with system specification. You decide on what? Circuit components. What type of what type of technology you are using. It's whether you are going to use transistor or MOS or something like that. Bipolar or CMOS and so on. So system specifications. Then what? IC circuit components. Then what? You decide on what? You decide on the architecture. Clear? You decide on our architecture, which we'll discuss in the next set of charts, and technology choices, and so on and so forth. You decide on device modeling. Now, in this class, the TA will give you the model. The model for the transfer will give it to you. But in reality, you need to choose the right model for the what? For the application. Then you need to create what? You need to do the CAD simulation. CAD stands for what? The computer-aided design simulation, to verify that you have satisfied all the specifications. If not, look at an angry face. It's not, which means what? You did not satisfy it, then you what? You go back and what? Try to tweak a little bit of the system specification. Clear? Tweak a little bit of the system specifications. Or you what? You change also the what? The device modeling. Use different device modeling, and so on. Now, if everything is okay, then you what? Then you decided to what? To start laying out your integrated circuits and fabricate it and then do some measurements. If everything is okay, you are happy. If not, you need to go back and what, by the way, you might go back all the way. You might go all the way back to the what? To the redesign. In other words, choose different what? Different circuit components or something like that. The worst part, by the way, is this one. Why? Because it means that you went through all of this and then you figure out what? That it's not what? It's not working for some reason or another. You have to go back to here. 544 is this. This is 544. Clear? Which means what? We will choose the type of architecture, we will choose the circuit components, we will what? We will conduct the analysis, both analysis and what? Simulation, circuit level simulation, to see if it satisfies the what? The given specifications. But we will not go over the what? We will not go over the rest. This is on another course on what? On circuit design or circuit layouts and some like. I don't know if there are such a course in USC. I'm not sure of that. Clear? Okay, good. So this is the circuit wireless simulation. Again, developed. I just explained this one to you. By the way, when you perform analysis, you need to perform a trade-off analysis. A lot of trade-off. A lot of trade-off. Increase amplifier power a little bit, decrease noise here, there, and so on. So let me show you a diagram so that you can get the idea. Huh? This is what they call it, the octagon. Octagon means what? How many sides? 8 sides. Clear? 8 sides. The noise, trading noise with linearity, with gain, with the power supply, with the voltage swings. Voltage swings means what? Peak to peak. Voltage swings with the speed, which means what? Data rate. With the I/O impedance, input impedance, output impedance, with the power dissipation, both DC power and what? AC power. All of these parameters are what? Can be what? Traded together. They can be traded between each other. Clear? And we will study it in detail, all of them, but we need first of all to understand what they are. Are you following right now? Noise. So what is noise? Linearity. What does linearity mean? But this is what I meant by what? Trading parameters within the design. Which one is more important to you? Which one is less important to you? And so on. So, we'll get to that shortly. This is a future, what is known as a future wireless network. You see, by the way, the whole idea is to what? Is to provide for ubiquitous access, ubiquitous transmission, whether you are indoors, whether you are outdoors, whether why is this one so, yeah, whether you have sensor net, for example, here you do have what? Several sensor networks. Notice, by the way, this is an ad hoc type network. There is no what? Access point. There is no what? Base station. So they are going to what? Each one will behave as a what? As a relay. Relay. One sensor will relay the information to another sensor and so on and so forth, all of it. This is on the highway communicating between the cars and what? Base stations. The base stations are connected to what? Towers on the building, wireless antennas on the building communicating with this, indoors and so on and so forth. Clear? But this is not part of what? Our course. This is EE, if you are interested, EE 597. EE 597. EE 597 deals with what? With wireless networks. In our course, we deal with what? Wireless transceivers. Clear? Physical layer stuff. Clear? And of course, I encourage you strongly to consider taking this whenever the class is offered. 597. This is the technical challenges. Look at the radio. It's no longer what? A single standard. Look at this radio. What do you see? You see the WiMAX. You see the wireless LAN. You see the direct video, digital video broadcaster. Are you following or not? You see, for example, AM, FM, radio, XM, what does XM means? Satellite radio. This is a paid service, Satellite radio, Bluetooth, and so on and so forth. Cellular, and so on and so forth. Now, what do you notice in here? You notice in here that each one of these standards uses different what? Different band. So your receiver has to have a what? Has to have a wide band covering what? All of these services. All of these services. By the way, you see the multiple antennas? Multiple antennas is what we refer to as a what? As a MIMO, the multiple input, multiple output antennas, and so on and so forth. The spectrum is already what? It's already very precious commodity. And this one needs to be able to what? To operate in all of these. Demands diverse applications, reliability, ubiquitous coverage, seamless indoor, out. Seamless, what does seamless mean? What is it? Without what? Without breaking the connection. In other words, you are indoor, you are making a call indoor, you go outdoor, you need to be able to what? Continue the connection. Seamless means what? You don't need to what? Retune your radio and something like that. Automatically, it has to be done that way. The device challenges, again, the size, the power, the cost, especially the power. Because these are what? Mobile units. These are handheld units. They are not going to be powered from a what? A power supply. Clear? From a power supply. All the power supply coming from a battery. We have multiple antennas, how we integrate them, multiple radios integration, coexistence. What does coexistence mean? Can 2 or more services coexist in the same vicinity without interfering with each other? Clear? All of these challenges are what? Especially in what is referred to as what? A multi-standard. Multi-standard means what? Supporting multiple standards? Yes? Yes? Okay, multi-band means what? Multi-band, when we say multi-band, what does it mean? A single standard that operates in what? Multiple bands. And then collectively we call it what? Multi-mode. Multi-mode means what? Means all of these are I mean, you know, they are multi-standard and what? Multi-band. Clear? All of these challenges faces the RF engineers to worry about all of them. And we will study them in detail as we move along. One possible solution is to do what? Is to do the reconfigurations of your radio via what? Software. You follow me on now? Via software. Now, what do? When we do, in other words, replace all of this by what? By a series of A to D. What is A to D stands for? Analog to digital converter. The problem with, by the way, what is involved in analog to digital converter? What are the three steps? The first step is what? Sampling. The second one is what? Quantization. The third one is what? Encoding. Now, what is the problem? The problem is that where are you going to put this AD? A pure software radio. A pure software radio. Notice what word did I did not use? I did not use defined. A pure software radio, those A to D are connected to where? To the antenna. Did you understand what that means? Means as soon as you receive the RF signals from the what? From the antenna. Let me show you a diagram so that you can see my point. Is it here or in? No, it's not here. This is in the next set of charts. I will get back to it shortly, but I want to show you one thing. Huh? I want you to see this. We'll get to this later on in detail. But tell me, is this a software radio or is it a software-defined radio? Is this one software-defined radio? Where? Why? Where do you see the ADC? Where do you see the ADC? You see the ADC in here after the what? Where are you sampling? At what frequency? The IF rather than in the what? RF. Is that easier or harder? Easier. Why? Because Nyquist, you remember Nyquist? What did he tell us, Nyquist? In order to be able to recover the analog signal from its samples, we need to sample at a rate of what? At least twice the highest frequency component being sampled. Yes? Now, if you are going to do the A to D immediately at where? At the antenna, you are dealing with what frequencies? RF frequencies, which are what? In gigahertz and up. Are you following me on that? Which means what? The A to D needs to what? Needs to be very fast. Are you following me on that? And you need to come what? You need to come up with an accuracy, an ADC accuracy of at least 14 or 15-bit ADC. Do you understand what 15-bit ADC means? What does it mean? When we say, for example, 15-bit. It means what? It means the encoder for every what? For every sample, you are representing it by what? 15-bit. Which means how many levels do you have? 2 to the power 15 output of the quantizer. The design becomes a little bit what? More complicated. So if you look at this, tell me here, we'll get to this later on. Where did I put the ADC? This one is still analog. Do you agree? The RF, the amplifier, LNA, and the what? Mixer are still what? Are still analog. Where is the digital come? The digital comes in here. Now, why do we do that? We do that because so that I can do what? I can do all the demodulation and the processing and stuff like that in digital domain. In digital domain, it takes what? Less space, less power, and so on. So all the advantage of digital that we talked about, you will get it. Clear? So when you hear the word software-defined radio, it means what? It means you are sampling, but not at what? At the RF. You are sampling possibly at the what? At the IF. Clear? If you hear the word what? Software radio, that's a pure software, which means what? All of it to what? All the way to the RF. Now, but what is the beauty of these types of radio? The beauty of these types of radio is that it is very easy to what? Reconfigure software, reconfigure all of these bands via what? Software, reconfigure the circuit, reuse it, because most of it are what is in software rather than in what? In hardware. Did you get my point on that? And we will talk about this shortly when we get to the next set of charts. However, we cannot spend too much time on this. This is totally separate class by itself. Now, I'm trying to see if the department can offer a class on software-defined radio, maybe in the summer or something like that. I haven't heard from them yet. I submitted a proposal, but I need to wait for them to see what they say. Clear? Clear? Oh, so one way to deal with this is that instead of using hardware for all of these multi-bands, I will use software, and I reconfigure these. Clear? Oh, the cognitive radio is even harder than this, because the cognitive radio needs also to be equipped with with sensor devices to figure out what bandwidth is available or not. Let me show you a diagram. We'll get to it later on, but just to see this. So that, by the way, I want you to see this. Just an example. You remember the crowd spectrum? This is measurement. This is from a measurement. Tell me, what do you notice? This is a spectrum, a given spectrum that is assigned a license to a to a primary user. Is he using it all the time? You can see there is a lot of There is a lot of empty space. Are you following or not? There is a lot of empty space available in there. Oh, now, let me show it to you so that you can see what I'm talking about. Look what we have here. By the way, those empty space is what we refer to as spectrum holes. Look what he does. Look what the cognitive radio does. He is operating, first of all, at this frequency. Why? Because it's a hole. Now, suddenly, a primary user came. So what does he do? He sends the medium, and he figure out that a primary user is sending. What did he do? He jumped to another Another hole. Hole means what? By the way, is this one licensed to somebody else? This one also is licensed to somebody else. But at that time, it is It's free. So he jumps to here. Then he jumps to here. Here. Are you following or not? Keep jumping back and forth, depending on where is the hole that he is sensing. Clear? So he tried to He tried to save on Save on the, it does not need extra bandwidth. Clear? And we will talk again. By the way, you can see from this chart that what drives the software-defined radio is that if you remove If you remove some of deregulation. Deregulation means remove some regulations. Loosen up a little bit. The regulation is very tough. You try to loosen up to provide for progress in the design of software-defined radio. This one will enable cognitive radio. And once you get to cognitive radio, this one will enable deregulation. In other words, you don't need to put you don't put regulation, because the radio is able to sense whether there are primary users or not. And if there is a primary user, he might not send, which means he is not causing any interference. So you don't need to put severe regulation. Did you get my point or not? But we'll talk about that shortly when we get to the architecture and the advantages and disadvantages. But again, we cannot spend too much time on these two. The emphasis will be on the actual designs. Clear? Not software design, but hardware design. Clear? Oh, now, evolution of wireless systems. You already know about these, the 3G and the wireless LAN. By the way, currently, the wireless LANs, the 54 megabits per second, the 802.11, 802.11G. Yes? Now, I want you to remember always, whenever they talk about 54 megabits per second, is that for a single user or aggregate? That's the aggregate. If it happens only one single user is using it, then you are going to get 54 megabits per second. But if there are aggregate users, this is This is the aggregate rate for all of them. Are you following me or not? Okay. And always remember, when we talk about 54 megabits per second for the wireless LAN, we are only talking about the wireless link between Between your mobile device and and the access point, or the router, or the wireless router. We are not talking about end-to-end. We are not talking about long distance, shorter distance. But you could also provide for example, for generation wireless LAN, the 3G cellular. How come in here we can support We can support longer distance. By the way, do you see the rate? Compare this rate. This is 3G. This one is The wireless LAN. How come this one is lower than this one? Much lower. Always remember the rule of thumb. The longer the distance, the rate will go Will go down. The rate will go down. Is that good or bad? That's bad. Are you following? That's bad. But what can we do? When the RF signal propagates, it will lose It will lose its strength. Oh, the 4G can go all the way to 4G can, or the one that's based on the OFDM. OFDM stands for Orthogonal frequency division multiplexing, MIMO, multiple access, multiple input, multiple output, and or the LTE. LTE stands for Long-term evolution. Long-term evolution, by the way, even for voice, it's going to go through Through the internet. Everything is IP based. Did you get this or not? See, currently, if you do have 2G or 3G, and you make a phone call, not a data call, but a phone call, is going to go through who? To the PSTN, to the public switch telephone network. But in the 4G, everything will go through the what? Everything will go through the internet. Clear? Okay. Now look at the rates. The new one, for example, for the wireless LAN, 450, 600 megabits per second. Big increase or small increase compared to what? 54 megabits per second. But something has to give. What is it? The distance becomes even what? Smaller, shorter and shorter. Clear? A 4G, 50 to 100 megabits per second, or the WiMAX, and so on and so forth. Now, what enhances the technology? All the improvement in what? In the hardware design, in the battery lives, and so on and so forth. It's more bandwidth, using adaptive modulation. What does adaptive modulation mean? If you can sense that the medium is what? Quiet. By quiet, I mean what? Not noisy. You can use modulation techniques that are what? That can cram a lot of bits per second on a what? On each hertz. This is what we refer to as what? Bandwidth efficiency. But suddenly, if the environment becomes noisy, you can what? Adaptively change what? Change the modulation into what? Into lower level modulation, so that you what? You reduce the amount of bits per second per hertz. What you need is what? What you are saying, that I would like to be connected all the time, but the bandwidth is okay to what? To change a little bit. This is what is known as VBR. VBR stands for what? Variable bitrate. Variable bitrate means what? Means you try to be what? Always time on. You don't want to be disconnected, but the rate, if it changes a little bit, it's okay. You can tolerate. Clear? But we'll talk about that, all of it, later on. Network resource allocation and so on and so forth. Quality of services. Yes?
Is it true that it's easier to tap into LTE because it goes through the internet than tapping into 3G and 2G?
Because the internet can support what? Can support both voice and data, but you are not going to get the same quality. You are going to get what? You are going to get higher what? Higher rate because of your electronics, not because of it is the internet. Going to the internet, you are going to be what? You are going to be the quality will become a little bit lower. But if you want to get access tapping, yes, it is, because in here, in 2G and 3G, you need to connect to the what? To a mobile telecommunication center, MTO, we call it mobile telecommunication office, before you go to the what? PSTN. Can you tell me why? Can you tell me why? In your 2G, you need, first of all, to access what? A mobile telephone office, mobile telephone center, yes? Before you go to the PSTN. Not only on the receiver location, but your mobile, the PSTN does not have a what? Does not have ability to communicate with you in wirelessly. I'm not sure, did you get the point? Did you get the point or not? You need, first of all, to connect to a what? To a mobile telephone office. And then the mobile telephone office will what? Will relay it to the what? To the PSTN. But if you are going to access what? If you are using LTE, you can access the internet from any service provider that is providing you with the service. Service providers are all over the place. Did you get the point? Did you get the point? Okay, good. Oh, now, some trading, this is, by the way, the growth, by the way. Most of the applications for wireless is what? Is now based on data. It's overcoming the what? The voice. And the problem with that is that the data is what? Bandwidth hungry. Whereas the voice is what? It's not bandwidth hungry. Anybody knows how much each voice call mobile takes? How many bits per second? 8 kilobits per second. Are you following me? 8 kilobits per second compressed voice. Yes? Is that high or low? Relatively low. Every phone call. But the data is what? Is bandwidth hungry. Clear? And when you hear the word what? Spectrum what? Spectrum reduction. Are you following? Which means what? You are running out of what? You are running out of spectrum. This is how much you need. This is how much extra spectrum you need to support what? To support the extreme traffic. Why? Because they want to increase. Look at the revenue. This is the revenue. The traffic demand is this. They want to go what? All the way here. Are you going to support this demand of traffic to get more what? More revenue. Clear? Okay. This is again the trade between what? Mobility and rate. As you go this way, what does mobility mean? As you go this way, a small mobile, Are you on mobile, for example, you are in a past trains or in an airplane and so on and so forth. What happens to the rate? As you increase mobility, what happens to the rate? It goes down. Are you following that? If you are fixed or pedestrian, the rate will will become a little bit up, because of mobility results in additional Doppler effects and so on and so forth. You are not going to have that problem if you are if you are in a fixed wireless access. Clear? Clear? Oh, this one is rate versus coverage. We already know that. As the range, as the range, look at this, Zigbee, Bluetooth, ultra wideband. This is cover limited limited range. Are you following? If you want to cover wider range, you need to go into into 3G, 802, for example, .11n, and so on and so forth. But what does power means? Huh? No. This one here, as you go this way, you need to increase the power to to provide for wider coverage. Are you following? That's the price you pay. Clear? Okay. This one is data rate versus frequency. What do you notice, by the way? What do you notice? Now do you see why they would like to go into into higher frequencies? The higher can you tell me why? Excellent. When you go into higher frequencies, these are what? What are these? 5 gig, 6 gig, what are they? These are the carrier frequencies. As you go higher in the carrier frequencies, the bandwidth becomes becomes wider. As the bandwidth becomes wider, the data rate becomes higher. Let's see if you have seen this before. Do you have heard about Shannon? Shannon, what did he say? He says C, which is let me write it here. Don't worry about this right now. I just this C is the channel is equal to W log to the base 2 1 plus S over N. And what did he say? He say you can transmit at any rate. You can transmit at any rate reliably. Reliably with probability of error approaches 0, as long as as long you don't exceed the channel capacity. And what does the channel capacity depend on? It depends on the bandwidth. That's the channel bandwidth. W is the So to increase the capacity, what do I need to increase? Bandwidth. A larger bandwidth means I can transmit at a faster rate. What else does it depend on? Signal to noise ratio. Why? The log is is a monotonically increasing function. So as you increase the argument of the log will also increase, increasing the signal to noise ratio. Now, can I increase the signal power indefinitely? No, but can I, ingenuity of an engineer, whether it's a system engineer or RF engineer or whatever, can you reduce the amount of noise? You can reduce amount of noise from your design. So reducing the amount of noise means Signal to noise ratio will go Will go up, hence this one will Will increase. Clear? Okay, good. So this is the data rate, the ultra wide band, and so on and so forth. All of this, the wider the band becomes because the data rate becomes higher. This is This is the range versus the frequency. This is the range versus the frequency. What do you notice? What do you notice in here? As the frequency increases, the range decreases. Now do you see why operators would like to work, that they don't want to work in much higher ranges, much higher frequencies, even though the spectrum might be available. Even though they might be available, but the higher the frequencies, you are going to end up with You are going to end up with lower Let's see if you remember. No, we did not discuss this yet, but let me just explain to you. Aside, this is aside. Let's see if you have seen this in the previous classes. The received power is equal to PT. What is PT? Transmitted power times GT. What is GT? The gain, transmitter antenna gain. Yes? Times GR, which is the receiver antenna gain. Yes? Over Or excuse me, or pi d over lambda, the whole thing, Now explain it to me. By the way, anybody knows what this equation is called? Somebody said it correctly? Friss equation. That's the Friss equation. We'll talk about that in detail shortly. And then from it, by the way, we will understand how we create link budgets and designs and so on and so forth. Okay, so one more time. PT is what? Transmitter power, transmitter gain, antenna gain, receiver antenna gain. Yes? D, distance between who and who? Between the transmitter and the what? And the receiver. Now in here, by the way, later on we need to see, now if we do have a base station like this is a base station, and this is a mobile station. Is the distance from here to here, or is it the distance from here to here? These are not the same distances, but we will study this later on. But did you get my point here? Is the distance horizontal on Earth, or is it antenna to antenna? Okay. Now, where is it? What is D? D is the distance. What is lambda? Lambda is the wavelength, which is what? Lambda equal to what? C over what? F. Yes? Now, let's see what happens here. As you increase F, what happens to the lambda? Decreases, decreases, increases, decreases. Which means what? The coverage becomes what? Smaller and smaller. Because the received power what? Now, why, I mean, why do you let it decrease? So what? Remember what I told you last time? We'll study it in detail short. A parameter of RF design is what is known as what? Sensitivity. Sensitivity, sometimes they call it what? MDS. Anybody? Anybody? Minimum. Very good. Minimum detectable signal. Which is what? How weak? How weak? What is the weakest signal that can be what? That can be detected? When I say that can be detected means what? It can be differentiated from background noise. Clear? If this one goes down, 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 and down, it might not be what? Detected anymore. Are you following that? Which means what? The coverage has what? Has stopped. Clear? So as you increase the frequency, keep that in mind. As you increase the frequency, the coverage will go down. Power dissipation, of course, as you increase what? As you increase the frequency, the power dissipation becomes what? Becomes higher and higher. Clear? Clear? You notice, by the way, even in your PCs, you notice that the what? That the frequency or the clock has already what? Has already saturated. You know, the integration of transistors and stuff, you keep putting what? More transistors on a single chip, but the speed is what? Relatively what? Have what? Saturated. You are not following me? I'm talking about the PC, about your processor. Your processor. You will see that the speed has what? Relatively what? A process. It's not increasing indefinitely. Are you like according to Moore's law? Clear? Why is that? Because as you increase the speed, you are going to need what? More power. And more power means what? Your devices will heat up. Clear? You need what? You need two cooling mechanisms. Clear? Okay, good. All of these trade-offs, we'll talk about them. I'm not going to go over all of these applications. Many. Wireless, broadcast, AM, radar, navigation, global positioning systems, remote sensing, RFID, the RF identification, electronic warfare, spies, and so on and so forth. Any medical, astronomy, automobiles, highway, like I showed you a moment ago, and so on and so forth. Endless. Endless application of what? For RF design or wireless design. Clear? That's the beauty of this. Okay. The trade-off, again, as I told you last time, is the bandwidth versus the power versus the what? The cost. Bandwidth efficiency is measured in what? Bits per second per hertz. Which means what? In a given bandwidth, how much bits per second can you what? Can you support? Power efficiency means what? Means how much power do you need? Minimum power. You need to achieve certain performance measure, which is what? Bit error rate. Clear? That's a power efficiency. Cost efficiency, of course, the cost of your machine. Clear? Now, you need to understand one thing. If you are designing, for example, a microwave link, a terrestrial link, line of sight, is the cost important or not that important? Why? Because it's a one-time situation. You are not going to manufacture on a what? Bulk basis. Did you get my point or not? Whereas in mobile, when you are doing mobile telephony or mobile unit, are you manufacturing 1 or 2 units or millions and millions and millions of units? millions and millions and millions of units. Then the issue becomes what? The issue of cost, the issue of power becomes what? Becomes very important. Do you follow me on that? So it depends on what? It depends on the volume of what? Keep that in mind. It depends on the volume of the application. Okay, now, finally, before we get into the next set of charts, finally, the design goals. On the transmitter side, what is the design goals? You are designing the transmitter. What are the goals? The first goal is what? Is that you need to make sure that what you have enough power to what? To provide for what? Desired coverage. So the first question is what? They must transmit at a specified amount of power while consuming as little power as what? Possible. Where is this, by the way, power coming from? We will see when we study the power amplifier. Actually, the power is coming from what? The DC and converted to what? RF power. Which means what? DC power to what? RF power. I would like that conversion to be as efficient as possible, using a small amount of what? DC power to generate the desired RF power. And I don't want what? A lot of loss, because loss means what? Heat. You want dissipated heat. Clear? Okay. So they must transmit at a specific amount of power, and they must not what? Interfere with transceivers operating in the vicinity. Clear? Adjacently. What does that mean? To make sure that your what? Your spectrum is confined within the desired band.
The time
Clear?
is 16 o'clock.
Okay. As the receiver, we deal with what? Several issues. By the way, you notice what did not deal with at the transmitter? I don't worry about what? Interference. Yes? I don't worry a lot about what? Noise. Clear? Now, would there be noise at the transmitter? We will see that one of the noise at the transmitter will be generated by the local oscillator at the transmitter. We will call it what? Phase noise. Clear? But in general, these problems results from where? Results from the receiver, at the receiver side. Clear? At the receiver side, I worry about it. Oh, so with the receiver side, what do I need to make sure the design goals is that they must be what? Very sensitive to what? To detect small input signals. The signals are what? Received weak. The receiver needs to be what? Sensitive to them. Clear? Sensitive input signals, probably as small as what? 1 microvolt. The receiver sensitivity, of course, is limited by what? By the amount of noise generated by the receiver and outside. In other words, source of the receiver noise is both. They must reject interference from what? Outside the desired channel, within the band and outside the band. Within the band and outside the band. Co-channel interference, we don't know what to do with them because they occupy the same what? They occupy the same band. What we are hoping is that the co-channel interference are with very little what? Very little power, which means what? They are located far away from me. They are far away from me so that their effect will be what? Will minimum. And of course, they must consume as what? As much or as small power as possible. We already went through this. Okay. Clear? God, it took us a lot of time to get to the overview. Now, let's get into the architecture. Not again, just overview. Before we get into each one of them, we need to understand each block of that receiver or that transmitter. What are the specifications? What are you going to be given? Clear? What are you going to be given? Oh, so the transceiver architectures. Again, the demand is for what? Low cost, small size, multi-standard, multi-band, like I told you a moment ago, low band, low power transceivers, and so on. So the RF interface. When you hear where is the RF interface, look at this diagram. The RF interface. We have the RF section and the what? The baseband section. Where is the baseband section here? This is the baseband section. We call it what? Backend. Everything here is what? Is digital domain. Including the demodulation, decoding, decryption, and so on and so forth. Demultiplexing. All of these processing is done in the what? In the digital domain. This is the front end. Attached to the what? To the antenna. Antenna is, for example, 900 megahertz to 5 gigahertz, whatever the case might be. What is the user end here? The user end will what? Will prepare the signal here to something which is more suitable to what? To the end user. Clear? Like, for example, a loudspeaker or what? TV screen in cases of videos and so on and so forth. Clear? Okay. So, remember, by the way, when we talk about baseband, what are we talking about? The spectrum is what? Around what? Around 0. Question, does it have to be symmetric around 0? Does not have to be symmetric around 0. However, it is much smaller than what? Than the RF band. Clear? Much smaller than the RF frequencies. One of the homework problems, you will see that the spectrum will look like this. Let's see if you can help me. First of all, is this baseband? That's baseband. Is this baseband? That's also baseband. Are you following or not? Okay, the difference between this one and this one is that this one has a what? Has DC in it. This one does not have what? DC in it, because there is nothing on what? On at F equal to 0. Clear? But is this an RF or is it the baseband? This is still a baseband. Why? Because this one here, from here to here, is much smaller than what? Than the RF frequency here. Clear? Okay, good. So, the baseband deals with what? The baseband range of frequencies of the information or the modulating signal. The bandwidth of the baseband determines the underlying rate at which the data can what? Can flow. Clear? So the bandwidth of the baseband is what? It will determine what? Will determine at what rate can you what? Can you transmit? Clear? Clear? Okay, good. Now, the RF section at the transmitter, again, what is the RF section at the transmitter side responsible for? Responsible for what? Up conversion, yes, the baseband signal to the assigned RF signal and injecting this signal onto the medium. The RF is the other way around. So in the transmitter is up conversion, at the receiver is what? Is down conversion. Back end, again, does the actual demodulation, decoding, decompressing, and so on and so forth. And the user end here, this one, converts the information to more suitable for the user. Clear? Oh, then we just did this design goals, repetition. Okay, let's look at the equipment, the component, each one of them. Antenna. Do we need an antenna? We need an antenna. Something has to what? There must be a component that will what? Translate an electrical signal to a what? Electromagnetic signal and vice versa. So the antenna is a what? Function of the antenna is to convert an RF signal from a transmitter to propagating. AM stands for what? Electromagnetic signal and vice versa at the receiver. What do you deal with? When you deal with antenna, what are the things that interest you? First of all, the operating frequency range. Yes? Now, if you are going to support all of these multiple standards, you need to have an antenna which is what? Which can cover or which can receive what? Wider range. Clear? Multiple antenna, operating frequency range. The size of the antenna, which again, as I told you, it's proportional roughly to the wavelength, actually 1/2 of the wavelength or even less. Clear? That's why you are using what? Higher frequency component, higher frequency RF signal, so that the wavelength becomes what? Small. Gain depends on what? Directivity. The more direct the antenna is, the gain is what? High. Clear? And now remember, I told you the beam, this be here, for example. This is called what? This is called the main beam. These are what? Side lobes. And these are what? The back lobes. Lobes. Clear? Omnidirectional. When you hear the word omnidirectional, what does it mean? It's in all directions. The gain is what? The gain is constant 1 in all directions. Clear? That's omnidirectional. Okay, directional antenna, of course, can provide you with what? High gain. You can also have what? Phased arrays, and you could also have what? Smart antennas. Smart antennas means what? Or phased arrays means what? Ability to, remember I told you, the signal is coming from what? From different angles. Clear? From different angles. Phased arrays antenna, it can what? It can combine all of these phases constructively. Clear? Constructively. Same thing with the smart antenna. Smart antenna can what? Can beam. Can direct the beam to the what? To the desired location. Clear? Can change it adaptively. Clear? Oh, and we will study this, but again, as I told you, this is a separate course. This is EE, but I forgot the number. 570? 571 or EE 573. One of them. One of them. And if you are really interested in RF, you should consider taking this class. And that's part of what? That's part of it. Filter. This is, by the way, another course, which is EE 541. Anybody taking this class? This is it. In other words, 541, only this. He does not look at, the course does not introduce you to the overall picture. Only what? Only the filters. Clear? Okay. Now, the filter is a how many port? We say what? 2-port device. What does it mean when we say 2-port device? Has an input and a what? An output. Clear? A 2-port device means has an input and an output. What is it? But by the way, where do we use them? Only at the transmitter or all over the place? All over the place. At the transmitter side and at what? Receiver side. Always remember, after a mixer, you need to have a what? You need to have a filter. No other way around. Okay. Different types of filters. What do we have? Low pass filter. These filters passes what? Low frequency components and reject what? High frequency components. Clear? High pass filter, on the other hand, is different. These are not desirable. Why? High pass filters are not desirable. Remember what I told you. High pass filter passes what? High frequency component. Why are they not desirable? Noise occupy what? The entire what? The entire spectrum. If you are passing what? High frequency components, a large percentage of the noise will what? Will go through the filter. Clear? It's better always to use what? To use low pass filter instead of the high pass. Band pass filter, it passes what? A certain range and reject all others. Band reject filter or a notch filter is the other way around. How do you sketch the characteristic of a notch filter? This is a notch filter. What is this? This is an F? What am I sketching? No. What am I sketching? What is this? What do I write in here? That's H of what? F. This is the frequency response. Okay, and what is it? Clear? Clear? Okay, this is called a notch filter. All pass filter. What is this all about? Have you seen this? Terminology. What does that mean? When we say all pass filter. What does that mean? So why are we using a filter? If it passes everything. Did you discuss this 541 or not yet? The guy who's taking 541. No. But have you heard about it? All pass filter? What is, by the way, can you sketch the characteristic of an all pass filter? No. The amplitude is what? The magnitude response, this is the magnitude response, is what? Constant, which means what? The amplitude is not going to what? Change. So what is going to change? The phase. The phase. An all-pass filter will alter what? Will alter the phase of the input what? Of the input signal. Clear? The phase will be altered. Clear? Depending on what you need. Depending on what you need. But the magnitude is not going to change. That's why we call it what? All-pass filter. All-pass filter means what? All frequency components will pass without amplitude degradation. What are, yes?
Why do we want to change the phase?
When you, for example, when you want to generate what is known as SSB, I will show you that shortly. SSB stands for what? Single sideband, as opposed to what? Double sideband. We will see when we get there, we will see that those two bands, the upper sideband and the lower sideband, they have the same information. So why are we sending them? We need only to send one of them. You follow me on that? When we want to send one of them, we need to do what? Phase inversion of the entire spectrum, so that then when we add them together, they will cancel with each other. You follow me on that? Now, we will also need phase conversion, which is much easier in the IQ modulation or demodulation. Remember IQ? We need a local oscillator as what? Sine and what? Cosine. Is that a phase change? That's a phase change. But this one is much simpler. Why? Because it's a single what? It's a single frequency. Whereas this one, I'm talking about what? Introducing phase difference over what? Over all frequencies of interest. Clear? That's the challenge. But we'll talk about that shortly. Please be patient. Now, what are the specifications of the filter? What do you specify in a filter? Let's see if you are familiar with this. Passband gain. What is that? What is that? Passband gain. By the way, it's in what units? In dB. Yes? Let's see if you can help me. Let's assume that this is a what? What type of a filter is this? Band pass filter. And let's assume that this is what? The center frequency. Yes? Where is the passband? This is the passband. Agree? Where is the gain? Now you might tell me, why is there a gain? It's a filter. The filter does not need to be a what? A passive filter. It could be a what? An active filter, which means what? It's actually an amplifier, but it's also providing for what? We call it a what? A tunable amplifier. Clear? It provides gain, but it also provides what? Channel selectivity. It select a certain channel. Clear? So when we say, for example, if this is the band, we will say that the passband gain or the maximum is this one, or the variation. Clear? The variation. It's in dB. Insertion loss. What does that mean? Insertion loss. When you put what? When you put the filter into the chain of blocks, you have a chain of blocks. When you insert the filter, that filter will introduce some what? Will introduce some loss. Because of what? Because of mismatches. Do you understand that or not? Mismatches. Now, we will see shortly when we talk about matching circuits, we will see that most of the matching circuits actually are what? Are LC circuits. LC circuits means what? It does not have what? Resistances in it. But that's easier said than what? Done. Because those inductors and capacitors already have what? Parasitic resistances in it. Did you understand that or not? And when do they have that? That will provide for what? Insertion. And it's also in dB. Clear? Okay. Out of band attenuation. What does that mean? Where is it here? Can you show it to me? Out of band. This is this attenuation. Clear? Okay. Cutoff frequency. What is that? The 3 dB, for example, cutoff frequency. Clear? The 3 dB. What does the 3 dB mean? 3 dB is when what? When the magnitude response fall to what? 1 over square root of 2 of what? The maximum. You notice I did not say 1 over square root of 2. I said 1 over square root of 2 of the what? Of the maximum. Everything is relative to the maximum. If the filter happens to be a passive filter, then the gain, maximum gain is what? Is 1. So we say what? The 3 dB is what? Is 0.707. Clear? Okay, keep that in mind. The bandwidth, how do I measure the bandwidth here? For this one, the bandwidth is, for example, F high 1 minus, F2 minus what? Minus F1. We call it what? A 3 dB bandwidth. That's the 3 dB bandwidth. Some people define bandwidth of a filter as what? The range in which what? For example, 90% of the input energy will pass through. You follow me or not? Yes or no? So you need to figure out what? How much bandwidth, where is the spread in the frequencies around the carrier frequency, such that 90% of the energy of the input signal will go through. Clear? Okay. Selectivity, sharpness, Q factor. What does that mean? This in the outside of the passband, how quickly this one is going to what? Roll. That's a measure of what? How sharp it is. Clear? And that will determine the selectivity. I don't want you to confuse sensitivity and what? Selectivity. These are two different things. What is sensitivity? One more time. We will define it in detail shortly. What does sensitivity mean? The weakest signal that can be what? Detected. Selectivity means what? How easy to select the desired channel among what? Among other channels. Are you following? Among other channels, how easy it is to what? To select the desired what? Desired selecting channel. What is the Q definition? We'll talk about this later, but for now, what is it? It's a center frequency, F sub C, the carrier frequency, divided by what? Divided by the bandwidth. Clear? Okay. The higher the Q, the harder it is to design. The harder it is to design. Yes, more complicated, costs more. And that is why I told you before that as the receiver, as we will see probably next time, we will see what? We will see that at the beginning, we will what? We will select the what? The band rather than select the what? The channel. We will leave selecting the channel to the what? To the IF, or even all the way to the what? To the baseband. At the beginning, we select the what? We select the band so that the Q is what? Relatively small. Clear? Okay, we'll get to that in shortly. How do we measure the sharpness or this in dB per what? Octave or dB per what? Decade. Question. What is dB per decade means? What does decade means? That means the frequencies are separated by what? 10. So for example, F is equal to what? 10. Another decade is what? 100, 1,000, and so on and so forth. Octave. Octave. 2. Octave is what? Is 2. Are you following me or not? Okay, we'll talk about that. Apparently, you are not familiar with it, but we'll talk about that. So when we say dB per octave means what? Every time the frequency what? Doubled. Did you get this or not? Every time the frequency is doubled, like 2, 4, 16. Are you following me on that? So on and so forth. Clear? Okay. Amplifiers. Did you understand the filters? Okay. With our interest, by the way, in this course will be only primarily on the bandpass filter and the what? And the low-pass filter. And those are the only components that we will not design. That's a separate course. You follow me on that? So whenever we use a filter, I will just write a block diagram. That's a different course. You need to take the other course. Clear? Okay. It used to be, by the way, these two courses used to be offered alternatively. In other words, one in the spring, one in the fall. I don't know why this semester they are both offered in the same semester. I have no idea. I don't make the schedule. Okay, amplifiers. Amplifiers, do we use them only on the transistor or on the receiver also? Different types of amplifiers. Power amplifiers. By the way, most programs in schools or whatever you want, when they give a course on the power amplifiers, they will always what? They will always tell you we run out of time. Did you follow me on that? In other words, they leave it till the what? Till the end, and they most of the time they don't even discuss it. But in our class, we will go into detail. Different types of power amplifiers, linear amplifiers, non-linear amplifiers, different types. Clear? We will talk about that shortly. So power amplifiers used at the output stage of the transmitter consumes, again, lots of power. Lots of power. By the way, in the transmitter, do we need to turn it off? I want you to tell me, do you understand this statement? Consume lots of power, so switching them on or off is what? Required. What does that mean? In your cell phone. The power amplifier. No, I don't think you understood my question. If you are not transmitting, if you are not sending anything, should your power amplifier be fully powered? What do you need it for? The receiver needs to be what? On, so that if somebody is what? Is calling you, they can get through. But the transmitter is only when you what? When you transmit. I'm not sure, did you get my point? Did you get my point or not? It's only when you want to transmit, you want to turn the power on. When you're not transmitting, what do you need the power for? And that's why I said switching them on or off is required. Low noise amplifier at the receiver. Most important to us, which is what? Which is to try to what? To strengthen the power of the received signal, which is weak, without introducing what? Without introducing a lot of what? A lot of noise. Clear? Okay, what does that deal with? Does it deal with selectivity or sensitivity? Sensitivity, because we are there. Remember, sensitivity is covered by what? Noise. Whereas the selectivity is covered by what? The nonlinearity. Okay, as we'll see in just a second. IF amplifier, by the way, do we have to have IF amplifiers? Of course, when we deal with what? Direct conversion or zero IF. Look at the statement. Zero IF. What does that mean? Zero IF means what? You go directly from RF to what? To the baseline. So you don't need IF amplifier. But if you need IF amplifier, if you do have an IF stage, you need a what? You need an IF amplifier. Remember what I told you last time, or maybe before. The gain at the receiver cannot be all achieved in what? In one stage. You are going to be able to, you need to what? You need to distribute your overall gain across the what? Across the receiving chain. Clear? Okay. So, the IF amplifier and so on and so forth. Amplifier provide for what? Power gain. Measured in what? What do we measure the power gain with? dB. Not dBm. dB. That's a power gain. Clear? Are they nonlinear devices or linear devices? They are nonlinear devices, which I'll show in just a second. All of this, by the way, we'll discuss them in detail. They're just an overview. Okay. What are the specs for the amplifier? Power gain. How do you define the power gain? How do I define the power gain? The power gain is the what? Is the ratio. If you are measuring it in dB, then it's what? 10 log. Of what? Of the power at output. What power? What power? The RF power. RF power, which means what? Which means what? The desired. Are you following me on that? The desired channel. The fundamental. Did you get my point on that? Divided, of course, of what? Divided by the input power. Clear? Noise figure, NF, also measured in what? In dB. We will see later on that we do have a noise figure in dB. If you measure the noise figure not in dB, then we call it what? Noise factor. But most of the time we will use only what? Noise figure. The higher the noise figure, the worse or the better? The worse. Are you following that? So, for example, if you say my noise figure is what? Is 15 dB or 20 dB, that means what? That device is what? Noisy. Clear? Clear? Okay. Now, we will see later on when we define, anybody knows how we define the noise figure? Is what? Is the ratio of what? The signal to noise ratio at the input to the what? Signal to noise ratio at the output. Yes? At what temperature? At room temperature. Clear? But we'll discuss this later on, not now. Let's not worry about it. Nonlinear effect, saturation. Let's understand all of these things. Let's see if you have seen this before. What am I sketching? That's the what? Input power. That's the what? Question. Is this a logarithmic scale? That's a logarithmic scale, which means what? This is in what? dBm. This one is what? In dBm. What does dBm stands for? dB milliwatt. Clear? dBm. In other words, dBm is equal to what? 10 log the power over what? A reference of what? 1 milliwatt. Clear? Okay. How does it look like? It looks like this. Clear so far? Okay, where is the saturation? This is the saturation here. Yes? Notice, by the way, there is a possibility even that it will go into what? Into compression. Did I show you this last time or not? It's a possibility that it will go into compression. Let's not worry about that. That's the saturation. Now, what is the first one that we are interested in? 1 dB compression. 1 dB compression. How am I going to denote that? P1C. P1C means what? 1 dB compression. Units? No. The dBm. This is a power. Are you following me or not? This is the power. What does that mean? What is this? What did I sketch? That's the linear portion. In other words, if my amplifier is what? Is linear, then it would be like what? Like this. Clear? Okay. I want you to see this. And I want you to see this. This one. Yes? So the deviation from the linear to the what? Saturation. Once this one becomes what? 1 dB, then we call this one what? We call this one as if whether, by the way, whether you look at it from the input or whether you look at it from what? From the output. Clear? What is this? From here to here. What do I call this one? That's the what? The power, 1 dB power compression as what? From where? From the input side. But on the output side, where is it? Clear? Clear? So the compression is what? 1 dB deviation from what? From the linear. Clear? No response. Okay, good. The higher this one is, when I say the power 1 dB deviation, the 1 dB compression, the higher it is. In other words, this point is what? Is here somewhere. Yes? What is that an indication of? The amplifier is what? Relatively very linear? Relatively very linear. Are you following me or not? Okay. Now, harmonic distortion. What does that mean? What is harmonic means? What is harmonic means? Harmonic means what? N, F0, F sub C, sorry, F sub C. Where N is equal to what? N is equal to 2, 3, 4, and so on and so forth. Clear? Okay, and when we say distortion, what is the units? Harmonic distortion. What is the units? dB, not dBm. Clear? Clear? And what is this? This is a ratio of what? The output voltage, for example, at what? At the second harmonic divided by what? Divided by what? Divided by the fundamental voltage. Clear? Okay, we'll talk about that again shortly. Intermodulation components is what? Plus or minus what? Clear? Okay. IIP. What does IIP stands for? Intercept points. Let's see what we have here. I'm going to sketch another curve here and tell me what am I sketching. What is this? Now, I want you to see this. By the way, this is linear here. This actually shaded, so it's not sketched. It's not sketched to scale. One second, one second. What can you tell me about this one and this one? No, this one is not very clear. One second. I messed it up. Tell me, what do you see, this line and this line? Which one has the higher slope? This one or this one? This one. This is the what? This is the third intermodulation power. This one is the what? The desire or fundamental power. By the way, it's as measured where? As measured at the output. Did you get this or not? Okay. Now, if this corresponded to the linear, yes, and this one also the linear portion, will they intersect? They will intersect. Did you get my point or not? What does that mean verbally? Verbally, what does it mean when they intersect? They intersect means what? Means the power in the fundamental component, which is the desire. The power in the fundamental component and the power in the what? Third order intermodulation components are what? Are the same. Did you understand what I just said or not? This power, we call it what? IIP3. What is the first I? The first I means what? Input. This is relative to the what? To the input. You didn't get it? Did you get it? Okay, by the way, detail and the analysis shortly. I'm just getting, where is the OIP3? Ah, very good. This one. Did you get it? Question number one. Are they related? What is the relation? In other words, what is OIP3? Units. No. The intercept point is not in dB. In dBm, it's power. Clear? This one is what? Can you tell me? IIP3? Agree? White plus. I'd say everything is dB. Yes? What, by the way, what is this? One more time. dBm or dB? dBm? dBm? dB. This dB. This not dBm. This dB. Yes or no? That's a gain. Clear? Clear? Question. I said question before your question, so I get the priority. Question. The higher the IIP is, the higher in the spec, if they give you a higher IIP3, is that a better linearity or worse linearity? In other words, is the device linear or not linear? If it gives you a higher IIP3, it's more linear. Are you following me? It's more linear, which means what? This point is what? Is somewhere what? Somewhere in here. Did you get my point or not? So the higher the IIP3, it means the amplifier is more what? More linear. You lost me? You did. But we'll get to the detail shortly. Yes?
Yeah, the GP here, is it the gain of the amplifier?
That's the gain of the power gain. Power gain, not the voltage gain. And all the gain, by the way, in this course, whenever I use the word gain, is a power gain unless otherwise stated. Unless otherwise stated. Everything is power gain. Clear? Clear? What is the slope of this one with respect to this one? This one to this one? 3. Are you following or not? That's 3 times the slope of this one. Why? Because this one is a third order intermod. If I want IIP2, how would the line look like? It look like what? The slope is somewhere between this one and this one. Clear? Okay. We'll do look at both of these shortly. And of course, you need to specify what technology you are. Yes, sir.
I see the math in the graph, but I don't see the design significance.
I told you, the higher the IIP3, it means what? It means that the amplifier is what? It's more what? Linear. If that point appear in here, what does it mean? It means, see, if they are linear, listen to me, if this is linear and this is linear, Yes? Remember, the slope of this guy and the slope of this guy is what? The slope of this guy is what? 3 times the slope of this guy. You follow me or not? The farther they intersect, what does it mean? It means that the saturation has not what? Has not started yet. And if it not has started yet, what does that imply? It implies that the amplifier is linear, which means what? It means that I can use it for modulation techniques that are what? The envelope is what? Non-constant envelope. Clear? Is variable. Clear? Now, we will put all of these together. Right now, I just want you to be familiar with the buzzwords. You think this is it? We are going to be looking at how we use it in the equation. Right now, I just want you to understand. If people talk about IIP3, I don't want you to say, huh? What does that mean? Did you get what it means? IIP3 is the input power or the output power in a way such that the fundamental RF power and the power in the third order intermodulation, not third harmonic, third order intermodulation components are what? Are equal. Clear? They are equal. That's the IIP3. Intercept. The II, input, intercept point, input. Input means what? It's relative to the input. Input, intercept point, which order? Third order. Clear? Okay. By the way, I thought you might ask the question, why is this one, the slope of this one is 3 times as this one? Yes? How come you did not ask that question? I will show it to you in detail. Right now, this is not it. We need to analyze all of this. Clear? So for time being, I just want you to understand the buzzwords. That's it. Okay. Now, mixers. Where do I use mixers? At both the transmitter and what? At the receiver. At the transmitter is for what? Up conversion. At the receiver, it's what? Down conversion. Clear? Now, if you are using a heterodyne, it's what? How many ports, by the way? 3 ports. Let's look at it a little bit carefully. Okay, let's look at the receiver. The transmitter is just the opposite. Let's look at the receiver. What is this port? This is called the what? RF port. What is this? This, the local oscillator. And what is this? IF port. Clear? 3 ports. Yes? Yes? Okay. Now, is the IF constant? Yes. The IF is constant. Is this one changing? This one changing, which means this one also is what? Changing. The difference between, in other words, what is the relationship? By the way, let's see if you help me here. Is the local oscillator greater than the RF power? The RF frequency or lower? No, I don't think you got my question. Concentrate. Let's take an example. Let's assume AM. What is the range of AM? AM. Amplitude modulation, AM radio. The range is roughly what? 600 to what? 1600 kilohertz. Roughly. 600 kilohertz. What is the IF? 455 kilohertz. Yes? Okay. Now, remember, mixer is going to generate what? What is the mixer? Is ideally, what will he generate? The sum and the difference. Why did I say ideally? Because in reality, it's going to change. It's going to generate what? Intermodulation components. Are you following or not? By the way, it will even generate harmonics. Is this a nonlinear device? Mixer? It is a nonlinear device because it's generating a new frequency component. Clear? So ideally, it will generate the sum and the what? And the differences. And of course, it must be followed by what? By a filter to select either the sum. You select the sum at where? At the transmitter side, and you select the what? The difference at the receiver side. How we accomplish this? Either by what? Nonlinear device, or by using a what? A time varying element. What does it mean when I say time varying element? Switching. The mixer will what? It behave as a switch, on, off, on, off, on, off. Are you following me or not? I will show you how we'll
5 minutes left, Professor.
Question? Oh. Yeah, thank you. We just started. So, I need you to explain to me one thing here. Let's assume, just for the sake of argument, the desired channel is 600. 600K. Yes? What should the local oscillator be? Remember, the IF is what? 455. In other words, this is what we have. I want you to understand this very carefully. This is the RF. What is this? What did I sketch, by the way? It's no response. No response. What did I sketch here? This is a desired channel centered around what? 600K. What does this, by the way, represent? That's the modulation, the AM modulation. Yes? That's the upper sideband, and this is the lower sideband. Agree? Yes or no? I want to shift this spectrum to where? IF, which is what? 455. 455. Yes? What do I use the local oscillator? That's the question I asked you a moment ago. Should the local oscillator be higher than this or what? Lower than this. By the way, both will work. Both will work. Do you agree? But I need you to understand the difference between them, because that is one of the decisions that you need to make when you design your RF transceiver, which is the following. If FLO, what does FLO stands for? Local oscillator, is greater than FRF. First of all, I want you to understand the terminology. We call it what? High side injection. Do not forget this. They ask about this in interviews and stuff like that. High side injection means what? Means the local oscillator at the receiver is higher than what? The RF. Yes? In this case, what should it be? In this case, in AM, what should it range from? Your oscillator, your local oscillator. In our example, I'm still waiting. It's what? 1015 all the way to what? Are you losing me or not? What is this range? When I write this range, what is that? That's the local oscillator range. That's the dynamic range of what? Of your oscillator, or the tunable range of your what? Of your VCO. Agree? This is called what? High side injection. Low side injection. If what? If FLO is what? Yes? Cannot hear you. What is the range here? What is the range? In our example? Help me. $145 to what? 1,000 and what? 45 kilohertz. Agree? Okay, what is the difference between them? Whether do you use high side or what? Low side. Can you tell me what advantage, disadvantage? Let's look first of all at the what? At the tunable range of your VCO. If you divide the high frequency over the low frequency, if the number is small, it's easier to design the what? The VCO. Did you understand what I just said or not? This is the range of what? The synthesizer. Yes? Divide this by this. What do you get? Approximately how much? 2. Divide this by this. How much do you get? Roughly what? 8. You follow me or not? This one is easier to design than this one. Did you get my point? Okay. But the major point in here is the following. This is now the local oscillator. Tell me, after you send it to the IF, how does the IF spectrum look like? Will it be folded? Will it be folded? I'm not sure. Did you get my point? The spectrum got inverted. You lost me here. Did you lose me? Did you lose me? The spectrum got inverted. How about here? Will the spectrum get inverted here? The spectrum did not get inverted. Now you might say, okay, so inverted. In some situation, these might not be what? Identical. In some other situation, some other modulation, if you invert the spectrum, the modulating signal might get also inverted. The 0 becomes a what? 1, and the 1 becomes a what? 0. But that might not be a major problem if you do have multiple mixing in the RF chain. Because, for example, if you do have two mixers in the RF chain, if this one inverted, the other one will what? Will invert it again. Did you get my point or not? I'm not sure did you get it or not. High side injection will invert your spectrum. Did you understand why is that? What is the difference between LO and this RF? Is what? Is IF. This one is higher than the RF, which means when you subtract this from this, the answer is what? Lower, which is this one. Yes or no? I'm going to run out of time quickly. Yes or no? Does this one invert it? The low side injection. This one does not invert it. However, this one results in what? In a harder design of your what? Of your VCO, because the ratio between the highest and the lowest is what? Is high. The dynamic range is what? High. By the way, the bandwidth is the same, but the generation of frequencies, the highest minus the lowest, or the highest divided by the lowest, the higher it is, it's harder to design the mixer. Clear? Okay. But I will show you that shortly when we get there. Okay. Now, the specifications of...
Sir? We are... I'm out of time. Sorry.
No, you don't need to be sorry, my dear. We'll continue next time. Did you follow me? Okay.
This concludes EE 544 with Professor Zahid on Thursday, January 23rd, 2014.